So in the last couple of videos we have talked about the types of chemical bonds that are formed. We talked about the characteristics of the compounds that are formed by those bonds. Today we're going to talk about how we draw a structure that represents these chemical bonds. All right, we call these Lewis diagrams or Lewis structures. We drew Lewis diagrams using dots to represent valence electrons. We did this for just elements. So you had the element symbol and the dots around it that represented how many valence electrons it had. We're going to still do that. Since valence electrons are the only ones involved in bonding, they're the only ones we care about, which means we use Lewis diagrams, those Lewis dot structures that we did, to show bonds. And this is done differently for the two types of bonds. So it's going to be done slightly differently for ionic compounds versus covalent compounds. So let's talk first about ionic bonds. Ionic bonds form when you have a positive and a negative ion. And as we talked about, the different elements, they have specific charges. So in order to do the Lewis diagram for a ionic bond, you have to first know the charge of each element that is involved. So you're going to have to look at the periodic table and know where it is and know what the charge of that element is. And once you know the charge of the element, then you can draw the Lewis diagram for that ionic compound. So when you have the periodic table, just to remind you, we have the columns are +1, +2, and then +3, plus or minus 4, -3, -2, -1, and 0. Those would be the charges of the elements by their columns. Now, all of these here in the middle have variable charges because they have the ability to have more than one valence. And when we get to examples of those, we will talk about that. So let's do a Lewis diagram example of an ionic compound, and let's choose a simple one to start off with. Let's choose lithium fluoride, LiF. So when we do this, I'm going to use blue for my cations and red for my anions. So lithium has one valence electron, okay, because it's in group 1. Fluorine has 7 valence electrons. Because it's in group 7. So what's going to happen is lithium is going to give up its electron over here to fluorine, and when lithium does that, it is now positive. It has given up an electron, so it has a +1 charge. And fluorine now is going to have all of its valence filled up. It now has 8 valence electrons because it has taken this 1 from lithium, and so now it has 8, but it has an extra electron, so it has a negative charge. And then those positive and negative charges attract each other, and you are left with your compound of lithium fluoride. So the way we do the Lewis diagram for this is we actually put in brackets the symbol for lithium, and we write its charge. It's positive. Now it is +1, and in chemistry we never write the 1, so we just write a plus, and then we're going to put in brackets the Lewis diagram for my fluorine. That's going to have all 8 of its dots that it has. It's got its 7 plus the 1 from lithium, and we put it in brackets, and we have its charge. So this right here is the Lewis diagram for lithium fluoride. So we simply move the dot for the lithium over to the fluorine, and so it has no dots because it's given it up, and we put it in brackets with its charge. And we do the same thing with fluorine. We have all 8 of its dots with brackets and its charge. Okay, that one's fairly simple. So let's do another example of an ionic compound, and this time let's do sodium oxide. So I have Na2 O. So this sodium and the 2 is telling me that there are 2 sodiums, and the O is, of course, oxygen. So sodium oxide. So if sodium is my cation, I have Na, but there's 2 of them. So I know I'm going to have 2 NAs. Now sodium is also in group 1, so it has 1 valence electron. And then I have oxygen that is in group 6, so it has 6 valence electrons. All right, and so what's going to happen is each of my sodiums are going to give an electron to oxygen, and that's going to leave my sodium with a plus charge, and this sodium is going to have a plus charge, and then my oxygen is going to have all 8 of its valence electrons because it got 1 from each of the sodiums, and so now it's going to have a -2 charge because it gained 2 electrons, so it's got a -2. So the way I'm going to write my Lewis diagram is I'm going to put brackets, and I have a sodium and it's got a plus charge, and then I'm going to have an oxygen with its 8 valence electrons, and it has a charge of -2, and then you're also going to have another sodium with a plus charge. So you'll notice that we alternated them. So if you remember our discussion of chemical compounds and the characteristics, these ionic compounds form these crystal structures that have alternating positive and negatives. So it's not always this incredibly simple, but this is a good way to draw it. So it lets us know that they're alternating and that there are 2 sodiums for each 1 oxygen. That's the ratio. All right. So let's look at one more example. Okay. So I'm going to do one where I'm dealing with a transition metal, something that's here in the middle and has a variable charge. Since I know the charges and the valences of all of those, how do I know the charges and the valences of the ones in the middle? Okay, so let's do CO2O3. Notice that's a lowercase o, so CO, that's cobalt, and this is oxygen. So what I'm going to do is remember the ratio. It means I have 2 oxygens for each of my 3, or 2 cobalts for each of my 3 oxygens. So we know that oxygen's charge is -2. I know that because it's in group 6. So oxygen's charge is -2. So there are 3 of them. So that's a total charge of -6. -2 times 3 is -6. Well, my overall compound has to be neutral. So that means that my cobalt has to cancel that out. So my cobalt has to have a total charge of +6. So the way I figure out what its charge is, if this is +6, well, there's 2 of them. So 6 divided by 2 means each cobalt has a +3 charge. So the way that I draw this out then would be I've got cobalt is going to have a +3 charge, which means it's going to be giving away 3 electrons, and there are 2 of them. So I have another cobalt that has 3 electrons that it's going to give away because it's going to end up with a +3 charge. And then of course my oxygens, I have 3 of them, and all 3 of my oxygens are going to have their 6 valence electrons. And let me draw these ones the way I draw all of the others. So let me take those away and make that the way I normally do it. Okay, so it looks familiar to you. So what's going to happen is I'm going to get an electron from this cobalt, an electron from this cobalt are going to go over here to this oxygen, and then that oxygen is going to get 1 from this cobalt and 1 from this cobalt, and then this cobalt's going to give up the others, and so my electrons are going to transfer over like that, and that's going to leave me
with a cobalt with a +3 charge, another cobalt with a +3 charge, because both of these cobalts gave away 3 electrons, and then I'm going to have my 3 oxygens with a -2 charge, because they each gained 2 electrons. So I have 3 oxygens with -2 charges. So to write out my Lewis diagram, I'm going to erase this real quick so I have room. To write out my Lewis diagram, I'm going to start with my oxygens, because there's more of them. So I'm going to have an oxygen that has its 8 valence electrons and a -2 charge. And then I have a cobalt with a +3 charge. And then I have another oxygen with all 8 of its valence electrons and a -2 charge. And then I have my other cobalt with its +3 charge. And then our final oxygen with all 8 of its valence electrons and a -2 charge. So this would be the Lewis dot diagram for CO2O3. So hopefully that makes sense. You simply know the charge, and so you know how many electrons get moved over. You can draw it out that way, but if you just know the charge of each of them, then you know that your anions, the negative ones, are always going to have 8 valence electrons around them, and your cations are not going to have any dots, but they are going to have their charge, and you put them in brackets. And that's how we do the Lewis dot diagrams for covalent or ionic compounds. Okay? So you've seen how to draw the Lewis diagram for an ionic compound using the brackets and the positive and the negative charges and moving the dots, and it's not all that complicated. For covalent compounds, it's a little bit more complicated, a slightly harder concept. So I'm going to give you some steps to follow. We're going to go through what these steps for drawing the Lewis diagrams are. Now these steps will give you a way of drawing most covalent compounds Lewis diagrams, drawing their structures out for most of them with a little bit of practice. You'll learn how to navigate ones that don't fit this steps exactly, but this will help you out with the majority of all of them. So let's dive into it. So the steps to follow. The first one is you're going to add up the total number of valence electrons available. That means all atoms involved. So if you got 5 atoms involved in your bond, you have to look at the valence electrons of each single atom, add those all up, and then if you have a positive or negative charge, you have to account for that. So let's say you add up all of the electrons and you have 20 electrons based on those elements together have 20 valence electrons, but you have a charge of +1. Well, that means you have 1 less electron. So if you have 20 valence electrons with a charge of +1, that means you actually have 19 valence electrons. And if you have a charge, normally would have 20 valence electrons, and the charge is -1, that means you have 21 electrons to deal with. So you have to account for all of the valence electrons available and take into account the charge of anything that you have. So if you have an overall compound that has a charge, which would be called a polyatomic ion, we'll discuss that more a little bit later. But if you have more than that, you're going to have to account for that charge. Then you're going to have to determine what the central atom is. Now this is usually pretty easy. If you've got something like H3P, all right, there's only 1 phosphorus and there's 3 hydrogens. So H3P, you're going to use P, phosphorus, as the central atom. So whichever one there's the fewest number of, you would consider your central atom. If you only have 2 things like CO, carbon and oxygen, if you just have those, then you have to choose the central atom would be the one that is the lower electronegativity. So the one that has the fewest number of atoms in the compound, or the element that has the lowest electronegativity. So in the case of carbon and oxygen, carbon's electronegativity is less than oxygen, so carbon would be considered the central atom. So you first identify and count up the total number of valence electrons, and then you identify the central atom and you write that down. Then we're going to attach all of our outside atoms to the central atom using a bonding pair. A bonding pair represents 2 electrons. That's why it's a bonding pair. We draw that with a single straight line. And I'm going to show you examples of all of these in a few minutes. I'm just going to go through the steps first. So you add up the total number of valence electrons, then you decide which one's the central atom and you write that down. Then you're going to attach everything to your central atom with a single bonding pair each. Then you're going to fill the outside atoms octets. So you're going to make sure all the outside atoms have a stable octet. Now hydrogen is the exception here. Hydrogen is full when it has a single bond pair already. So once I make a bond with hydrogen, hydrogen is stable. It's full because hydrogen, being the exception, it doesn't need 8. It wants to look like a noble gas just like everything else, but hydrogen wants to look like helium. Helium is a noble gas, but helium only has 2 valence electrons. So as long as it looks like helium, it's happy. So hydrogen is only going to share its 2 electrons there and have a single bonding pair. All other atoms in a covalent compound, you're going to have to give 8 valence electrons to the outside atoms. Now, all of these electrons that you're using are coming from that total number of valence electrons that you started with in step 1. So you're subtracting. When you run out of electrons, you can't fill any more. Okay? Now, if you fill up the octet of all of the outside atoms and you still have electrons left to work with, you're going to add those to the central atom. And once you have done that, you check the octet for everything. You make sure all of the outside atoms have a stable octet and the central atom has to have a stable octet as well. So you check the octet rule. If everything fits the octet rule, you're done. If it doesn't, then you might have to move electrons around and form double or sometimes triple bonds to make the octet rule work, to make sure the octet rule is satisfied for all atoms. All atoms have to have a stable octet. And remember, hydrogen has a stable octet with 2 electrons. Everything else has to have access to 8 valence electrons. Once the octet rule is satisfied and you've gone through all this process, then you're done. Okay, so these are the steps that if you follow these steps as you draw these Lewis diagrams, it will make it a whole lot easier and you will get the right answer most of the time. There are some tricks and some things to remember, but most of that comes with practice. So as you practice it and you'll see the differences, you'll catch on, you'll get it. But these steps are the best way to draw these Lewis diagrams for compounds. And so let's look at some examples and so I can explain how these steps actually work. In covalent compounds, the Lewis diagram is a little bit more complicated, as you saw. So we've gone through the steps. So now I'm going to use some examples to go through those steps again. So let's start with the compound HBr. So the first thing we need to do is determine the total number of valence electrons. So hydrogen is in group 1, so it has 1 valence electron. Bromine is in group 7, so it has 7 valence electrons. So that means I have a total of 8 valence electrons to work with. So I've determined my total number of valence electrons, and now I need to determine my central atom. Now hydrogen can never be the central atom because hydrogen is stable with only 2 valence electrons, so it can't form more than 1 bond. Therefore, it can never be the central atom. So bromine is going to be my central atom. So I have bromine, I write my central atom, and then I'm going to attach my outside atoms, that's the other things, to my central atom with a single bonding pair. And I do that with a line. Okay, sometimes you will see it written like this, where they just do 2 dots to represent 2 electrons. And this is fine, you can do it this way. I personally don't like it this way, but it is still correct. I prefer to use the lines because it is easier to see and makes more sense. So we have this. Now this line represents 2 electrons. So I just used 2 electrons, so I have 6 more that I need to place. I have to use all 8 of these electrons, so I've just used 2 of them, I have 6 more. Okay, so now we have to fill the octet of the outside atoms. Now, this is my central atom, this is my outside atom. What you need to make sure you always remember is hydrogen can only have 2 electrons when it is bonded with something else. So we never put anything out here on hydrogen. So the 2 here are already filling the octet of hydrogen. Its octet only needs 2. So that means I have to put all of the extra electrons on the central atom, and I always put them on in pairs. So that means I put my 6 electrons on in pairs. I've used all 6 of them. I only have 0 electrons left. So I check the octet. Bromine has 2, 4, 6, 8, because the ones in this bond count as 2, so that's 8. So bromine has access to 8 valence electrons, and hydrogen has the 2 valence electrons it needs. So the octet rule is satisfied, so I am done with the Lewis diagram for HBr. Now that's a fairly simple one. So let's try a few that are slightly more complicated. So let's use everybody's favorite compound, H2O. Okay, so I have 2 hydrogens and 1 oxygen. So let's look at the valences of these. So again, hydrogen, there is 1 electron, but there are 2 hydrogens, and then oxygen has 6 valence electrons. So 1 times 2 is 2, plus 6 is a total of 8 valence electrons to work with. So now I need to pick my central atom. My central atom is the one that has the fewest number of atoms. So in this case, oxygen. Oxygen will be my central atom because there's only 1 oxygen and there's 2 hydrogens. So I draw my central atom, and then I attach my outside atoms to my central atom using single bonding pairs. So 2 electrons and 2 electrons. So I just used 4 electrons, 2 here and 2 here. Remember, each of these lines represents 2 electrons. So I've just used 4 electrons. I have 4 left. So I'm supposed to put the extra electrons on the outside atoms. Well, hydrogen, again, does not need any more on the outside. So these 4 extra electrons go on my central atom using bonding or using electron pairs. So I put 2 paired together and 2 paired together. Okay, so I have used all 4 of those. I've used all 8 of my valence electrons that I had to start with. So now I need to double check the octet rule to make sure everything is happy and stable. So hydrogen, again, is happy with only 2. So this hydrogen is happy. Hydrogen here is happy with 2. So this one's happy. And oxygen has 2, 4, 6, 8. That meets the octet rule, so we are done with that one. So again, if you follow the steps, you're going to get the right answer most of the time, and sometimes it can be a little bit more complicated, as we'll see here in a second, but as you go through it and you practice it, you get a little bit better at it. So let's do another example of carbon tetrachloride, CCl4. Okay, so first we need to figure out how many valence electrons we have to start with. Well, carbon has 4 valence electrons. It's in group 4. Chlorine has 7 valence electrons because it's in group 7, but there are 4 of those. All right, so that 7 times 4 is 28, and plus 4, that means I have a total of 32 electrons to work with. Okay, 28 plus 4. So the central atom then is going to be the one that has the fewest number of atoms. Well, that's going to be carbon in this case. So carbon is my central atom. And then I am going to attach all of my chlorines to carbon using single bonding pairs. You'll notice that I spread them out because what they're going to do is they're always going to spread out as evenly as they can. Now on 2-dimensional paper like this is the easiest way to draw it, is to make this little plus sign, draw them kind of in a square type configuration. So what did I just do though? I just used 2, 4, 6, 8 electrons. So I just used 8 electrons. So 32 minus 8 gives me 24 electrons left to place. So I've done my central atom. I've attached my outside atoms to my central atom using single bonding pairs, and now I need to fill the octet of my outside atoms. So that gives me 1, 2, 3, 4, 5, 6. That chlorine is filled. 1, 2, 3, 4, 5, 6. That chlorine is filled. 1, 2, 3, 4, 5, 6. That chlorine is filled. And 1, 2, 3, 4, 5, 6. That chlorine is filled. And I just did 6 4 times, so I just used 24 electrons. I have no electrons left to work with, so all of them are placed where they're supposed to be. So now I need to check the octet. This chlorine has 8 electrons. Remember, this is 2. This chlorine has 6 plus 2 is 8 electrons. This chlorine has 6 plus 2 is 8 electrons. This chlorine has 6 plus 2, there's 8 electrons. And carbon has 2, 4, 6, 8 electrons. So all 5 of these atoms have 8 electrons. So the octet rule is satisfied. So I am done with my Lewis diagram for carbon tetrachloride. All right. So what happens when it's not quite that simple? All right. Let's do NH3, otherwise known as ammonia. All right, so nitrogen has 5 valence electrons. Hydrogen has 1 times 3. All right, so that's 3. That's 8 valence electrons. 5 plus 3 is 8. So our central atom is going to be nitrogen because there's only 1 nitrogen. And then hydrogen are my outside atoms. So I attach my outside atoms with single bonding pairs. And I am left with, I just used 2, 4, 6. Just use 6 electrons, so I have 2 left. So now I need to fill the octet of my outside atoms. Well, my outside atom is hydrogen, so the octet is already filled once I've made these bonds. Hydrogen is done. So I filled my octet, but I still have 2 electrons left, which means I need to place those extra electrons as a pair on my central atom. All right, and now I need to check the octet. Hydrogen, stable. This hydrogen, stable. This hydrogen, stable. Nitrogen has 2, 4, 6, 8 electrons. It's stable, it's happy. This is the Lewis diagram for NH3. All right, so hopefully you're seeing how the steps work. Now there's a couple of things in the steps that we haven't gotten to yet about what to do to make double or triple bonds. So let's do an example where that becomes necessary. So let's use carbon dioxide, good old CO2. How many valence electrons do I have? Well, carbon has 4 valence electrons, and oxygen has 6, and there are 2 oxygens, so that's a total of 12. 4 plus 12 is 16. So I have 16 valence electrons to work with. Now I need to pick my central atom. My central atom is going to be carbon, because there's only 1 carbon here, and I have 2 oxygens. So I'm going to attach each oxygen to my carbon with a single bonding pair. I just used 2 and 2, that's 4 valence electrons, so I have 12 left. And now I'm going to fill the octet of my outside atoms. So that's these 2. So to fill their octet, they each need 6 more. They have 2 from their bond, so they each need 1, 2, 3, 4, 5, 6, and 1, 2, 3, 4, 5, 6. So each of my oxygens get 6 more electrons. So that's 6 here and 6 here. I just used 12. So I have no more electrons to work with, so I cannot add any more electrons to this picture. All I can do is move them around. And why would I care about moving them around? Well, when I check the octet, oxygen has 2, 4, 6, 8. This oxygen is stable. This oxygen has 2, 4, 6, 8. This oxygen is stable. Carbon has 2, 4. Carbon's not stable. Carbon needs to have 8, but it only has 4. So what I'm going to do is I'm going to borrow from oxygen. So what's going to happen is carbon doesn't just share this one electron, or carbon and oxygen don't just share these 2 electrons, they're actually going to share 4 electrons. So the 2 they were already sharing plus these 2, it now shares 4. This is a double bond. Notice there are 2 bonds. It is a double covalent bond. It bonds twice. So this oxygen, you'll notice, it still has 2, 4, 6, 8. This oxygen still has 8 valence electrons available to it, so it's still stable. This one still has 8. Carbon now has 2, 4, 6. Carbon's not quite stable yet. So we're going to do that again, and we're going to share 2 more between that carbon and oxygen and create another double bond. So now notice this oxygen still has 2, 4, 6, 8 valence electrons, and this oxygen still has 2, 4, 6, 8 valence electrons. So the octet rule is satisfied with the oxygens, and so carbon now has 2, 4, 6, 8. Remember, each line represents 2 valence electrons. So it has 4 lines, so that's 8 valence electrons. The octet rule is satisfied, so we are done, and carbon dioxide is happy. All right? So let's give a situation where we have a triple bond. So let's use the diatomic nitrogen, N2. This is nitrogen combined with nitrogen, okay? So let's look at it this way. We have 2 nitrogens. Each nitrogen has 5 valence electrons. That's 10 valence electrons to work with. So I'm just going to pick, I have 2 nitrogens here. They're both the same, so it doesn't matter which one you say is the central atom. So I'm going to link them together. I just used 2 electrons. I have 8 more. Okay? So now I'm going to fill the outside. I'm going to choose the right one as the outside. Fill the outside, so that's 1, 2, 3, 4, 5, 6. I just used 6 more valence electrons. I have 2 left. The outside atom is full. I still have 2 left, so I'm going to put those 2 on the central atom, and I have used up all of my electrons. Okay, so this nitrogen is stable, but this one is not. This one has 8. This nitrogen only has 2 in the bond and 2 out here in this lone pair. So that only has 4. So what I'm going to do is I'm going to borrow and make another bond. So now this nitrogen has 6, 2, 4, 6, and the right nitrogen has 2, 4, 6, 8 still. So the one on the left is not stable yet, so I'm going to make another bond. All right, so now I have 3, so 2, 4, 6, 8, and 2, 4, 6, 8. Each of my nitrogens are now stable. They each have 8, so the octet rule is satisfied. So that is the Lewis diagram. Now what you need to recognize and understand though is that you're never going to have more than 3. There's no such thing as a quadruple bond here. We have single bonds, we have double bonds, and we have triple bonds. You're never going to have a quadruple bond here. So you're not going to have 4 bonds between 2 atoms. So that is that one. Let's do one more, slightly more complicated. All right. I have N2O3. Now I'm going to do this using the rules and the steps that I've shown you. It's not 100% accurate with the way the chemical actually forms, but for a basic chemistry class, this is a good enough understanding for what we're doing. So I'm going to start with filling out the total number of valence electrons. So again, nitrogen has 2 valence, or 10. Nitrogen has 5 valence electrons, and there are 2 of them, so that's a total of 10 valence electrons from nitrogen. Oxygen has 6 valence electrons, and there are 3 of them, and 6 times 3 is 18. So that means I have a total of 28 valence electrons to work with. So then I need to pick the central atom. Well, I'm going to say nitrogen is my central atom because there's 2 nitrogens and there's 3 oxygens. So I have my nitrogen, and now what I'm going to do is I'm going to attach the other nitrogen and all three of my oxygens. Okay, so I've attached my outside atoms to my central atom, and I just used 2, 4, 6, 8 electrons. So I have 20 electrons left. So now I'm going to fill the octet of my outside atoms. So I do 2, 4, 6, 2, 4, 6, 2, 4, 6. So my oxygens are all filled, and I just used 18. So I only have 2 left to put on this nitrogen. So again, I cannot use more than those 28. So these are all the electrons that I have. So you should be able to see that the oxygens are all stable, the middle nitrogen is stable, but this one is not. Okay? And forming a double bond here is not really going to help. And so what am I going to do? So what actually happens in this case is, instead of having a single nitrogen as my central atom, what I've just discovered is that both of my nitrogens are central atoms, and one of those oxygens is actually attached to the nitrogen there. Okay, so what does that do for me? Well, that gives me, I haven't used any extra. All I did was shifted and moved that one over. Okay, so now I can make a double bond between the nitrogen there, and that gives me 2, 4, 6, 8 on oxygen, 2, 4, 6, 8 on nitrogen, and this oxygen has 8 and this oxygen has 8. So everything's stable, but now this nitrogen only has 6, 2, 4, 6. So one of these two oxygens, I can make a double bond with that nitrogen, and so now I have 2, 4, 6, 8 there, 2, 4, 6, 8 here, 2, 4, 6, 8 there, 2, 4, 6, 8 on this nitrogen, and 2, 4, 6, 8 on that oxygen, and they are all now meet the octet rule. Now the one thing you need to recognize and understand is that this is one configuration of these. What actually happens is these bonds kind of switch around and go back and forth. This double bond isn't always between these two. Sometimes it's between these two, and so the bonds kind of shift around between them as they share. It's what we call resonance, which we're not going to get into resonance structures of covalent compounds in this class, because that is beyond the basic understanding of the way chemistry works. So this is a good enough explanation, and as long as you follow the steps that I gave you, then you should be okay on getting that. Alright, so now you have seen the steps for the ionic compounds. You've seen how to draw them with the brackets and the plus and the minus, and putting them together in an arrangement to give it that crystal structure. You've seen the steps and how to draw Lewis diagrams of molecular compounds. So in the next video, we're going to talk about how these molecular compounds actually form specific shapes, and we're going to talk about something called Vesper theory and molecular geometry. So thanks for watching, and have a day.